Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
All right, let's make a start. So, just a couple of quick announcements. I've got the assignment marks ready to go, but I've just got to get them checked by the main office. I've given them to the main office this morning, and they do magic with a spreadsheet. So they'll be up in the grade book either later today or early tomorrow. Tomorrow's lecture, first thing I'm going to do is I'm going to talk about the assignment. So I'm going to talk about what the grades mean and talk about what people might have done, what people did do and that kind of thing. So when you do get your grade from the grade book, which will be before we have that talk, my best advice is relax, okay? Relax. If you get your grade and you think, oh, it's low or whatever, don't immediately fire off an email saying help me, or you're a bastard or whatever, because it probably doesn't mean what you think it means, all right? So I'm going to give you some very brief summary statistics, and then we'll talk about it in much more detail tomorrow. I think it's marked out of 50, but getting 50 is not really possible, so it's not really marked out of 50. It's kind of, I think 40 would be the highest score anyone could imagine getting. What that means is things will get scaled in the end, so people should not be at all concerned about that. Leave that to me. I've been doing scaling for a long time, and it all turns out okay. The average score was about 25. Okay. Well, I told you, right? They're not going to be high. That's just the way it is. So the average score is going to be around 25. I think the highest score is around 36. I think the lowest score is around 10. Okay. Now, would I fail anyone based on that answer? No, right? No one who handed it in is looking at failing if this was the only piece of assessment, okay? So that'll give you an idea of how the scaling is going to work, okay? It's going to work, so 25 will get scaled. I think the average grade in the course will be around a credit, which is what normally happens. So everything is going to get scaled. Now, you're probably saying, well, okay, why don't you just give us highest score to start with? The answer is, scaling up is way easier to make people, feel happy than scaling down. So what I didn't want to do was mark them easy and then have to scale everybody down, because that just causes everybody to be very unhappy, okay? So I've marked them hard, okay, and so then the scaling will be up. But the good news is no one's going to fail. If you didn't hand it in, you might be in trouble, but if you handed it in, everyone did something, halfway reasonable, even at the low end, and so it's all going to be okay. So when you get your score, do not panic at all, okay? Do not panic at all. Tomorrow, or as soon as I get the clearance to put the grades on the grade book, I'll put them up. When you look in the grade book, you should see your mark broken down into 3 parts: writing, graphics and analysis. Okay, they add up to a number that'll be, nominally out of 50, but 50 is a dream, don't worry about that. And then you'll get some feedback. I think the feedback, I can't get the grade book to show the feedback without you just floating your mouse over it, and then it appears in a box that pops up like a little tooltip box. You've probably seen that before. And you'll be able to see your feedback there, okay? Then tomorrow, like I said, I'm going to talk you through the grades so that we can all be relaxed, and I'm also going to talk you through some things that you might have thought about but maybe didn't, or if you did, then whatever, okay? So, let's park that discussion right there. Thing number 2, so today's an interesting day. I got an email on Friday from someone over in marketing at the university saying that they want to take some photos of people lecturing, okay? So they said, could they take a photo of me? I'm flattered. Anyway, so at about a quarter to the hour at the end of this lecture, someone will come in and start taking pictures, okay? So I'll stop and let them set up. And I don't think they're going to take pictures of anyone's face or anything, so don't worry. and I think they mainly want to take a picture of me. I've dressed in marginally better clothes than normal because God knows what they're going to do with the pictures. And we'll see what happens. Okay, so that's going to happen in about a quarter. So don't be alarmed if someone comes in with a camera. All right. Okay, now let's talk about, since I'm doing announcements, let's talk about the roadmap, where we're at. So as I said, assignment 1's on the slate to talk about tomorrow. What I might do also tomorrow is talk a little bit about the project, okay, so that you guys can get started on that if you haven't already. So just, and to get people started if that's been an issue. So tomorrow I am going to speak mainly about the assessment that's going on. So it's one to come to, or one to listen to anyway. So be ready for that. After today's lecture, you should have everything you need to do assignment, well, don't assignment 1, the project, okay? Either data set. And then on Wednesday we'll start the time series stuff, which will get us going towards the last assignment, okay? Which is not a hard assignment, okay? And we'll talk about that as we go. Okay, so that's the roadmap for where we're at. We're on track, as it turns out. So today what we're going to do is finish off talking about the regression stuff, which is in Chapter 4, with the goal of tomorrow, all about assessment, and on Wednesday, start time series. Okay, so that's where we're up to. So let's finish off talking about regression. So we were talking about these stepwise procedures. And so you might remember we've got this cement data. So we've got 4 X's and 1 Y, and we're trying to choose a good model. And so we were using this stepwise, feedback there. We're using these stepwise procedures to deal with that. So I remember last time I showed you the exhaustive one. So I'm just going to make this window a little bit bigger so you can see the command here. Okay. So the basic command is in the Leaps library. So Leaps is what you'll need to install and load in order to run stepwise regression. The main command is reg subsets. In other words, find subsets of variables and fit them. You give it Y till the X, that's your model. Your data's here. Then the important thing is this method equals. And your choices are exhaustive, which will fit every model. That'll be fine if you've only got 4 or 5 X's, right? Even if you've got 6 and you're prepared to watch it scroll off the screen, you can go ahead and do that, okay? If you've got more X's and you want to have a bit of a streamlined approach, your 3 methods are forward, backwards, and this thing called sequential replacement. So let me again remind you what each of those 3 are. So forward, what it does is it fits, starting with an empty model, it fits models that have one thing in them, okay? Finds the best one of those based on something like R squared, adjusted R squared. Then at the second step, it tries to add a second variable, but it only adds to the variable you chose at the first step. So it's not exhaustive anymore. It doesn't fit every 2 variable model. It fits only those 2 variable models that involve the first one you chose. Okay? Then it chooses a second one. Now you've got 2 things in the model. Then it fits a 3 variable model, but only those 3 variable models that have the first 2, and so on. So it's an accumulative approach. Now backwards works in, and the way you do that in R is you go method equals forward here. We did that last week. F-O-R-W-A-R-D. Method equals forward. We'll do that. Okay? What does backwards do? Backward starts with the full model and removes things one at a time. And it removes it on the basis of what one least belongs there, right? What one provides the least explanation. And so it removes one variable, then it fits every 3 variable model, right? Removes the one variable it can remove. Then it fits every 2 variable model that's got the first one removed, okay? And so on down. So it basically takes a full model and works down to build a better model, all right? Or a smaller model that has better explanation. Now, both forward and backwards have the problem that there's no looking back, right? Once you've added something in, you can't get rid of it, even if it turns out later not to have been a great choice, okay? So the best analogy for that is it's like when you've got a bag of candy or a bag of lollies and you've got a little kid waiting for the lollies. Forward is like saying, right, I've got the bag, I'm going to give you the lolly you like the most, choose one, chooses from among the lollies, right? Chooses one, eats it, right? Then you say, okay, now choose the one you like second most. So that's the second step. It's already eaten the first one, right? So that second step is going to involve choosing the one that goes best with the first one, right? It's no good having a piece of chocolate and then choosing licorice, even if you like both, because that taste in your mouth ain't going to be too good, right? So that's how forward works, and you accumulate lollies until the kid says they're full. That's a kid, so they probably never say that, but anyway, until they're sick, and that's how you build up, right? Backwards is like you give the kid the bag, right, and you say, right, give me one back, and then when they give you one back, the one they like least, you eat it, and it's gone, right, and so on. So you work backwards. So the way sequential replacement works is a bit different. It's like you start with the bag and you say to the kid, okay, select the lolly you want the most, but don't eat it, right? So the kid selects the lolly they want the most. Now they're holding it. They're not eating it, haven't eaten it, so it's not gone. Then give me the one you want second most, okay? Then the next step is you say, right, now you've got two things there. You want to give me one back? Okay, which one do you think you don't want? They might say, no, I still want both of them. Okay. Third step, give them another lolly. Now I've got three. There you go. Do you want to give me one back? And so you go backwards and forwards. So if the kid makes a mistake, chooses something that's going to be a poor combination on eating, they can give you one back and make a secondary choice. Okay? And that can happen in model selection, right? And this happens in this data set, right? Because for this data set, when you go forward, the first thing it does is it chooses X3, right? You know, it's stuck with X3. But we know the best model for this particular data set has X1 and X2, not X3. But on forward selection, you don't have that opportunity. Once you've got X3 in the bag, right, you've eaten it. Too late, it's gone. Right? It's already there. So this sequential replacement lets you essentially iterate towards the best model by sequentially going backwards and forwards. So last week I blanked on what the method was called and I couldn't guess it. So I went upstairs, used the help. Actually I didn't use the help, I used Google, right? Because the help didn't help, which was a bit of a shame. But Google knows everything, as you well know. So I got the link that told me the answer plus a bunch of porn, because that's the way Google works, right? You get the link you want and then everything else. Because I didn't look at the other stuff, but I did find out that it was sequential repetition, SEQREP. So who was going to guess that, right? Who was going to guess that? Which is the beauty of R, of course. R is written by 1,000 people. Everyone's written their own library, okay? So you ain't going to guess what a thing's called because someone else just made it up. So that's what it's called, SEQREP, sequential repetition. So if I run that now, okay, do the summary, and then show you the table, okay, you can see, again, you're going to end up with the answer that has, so you run your finger down here and you get to this one, I think, yeah, 0.9744, and it's got X1 and X2 in it, okay, that's the one you end up with. So that's the way you use sequential replacement. So that's a little bit about these stepwise procedures. What do I recommend? Well, look, I guess realistically, if you've got a small number of X's, I guess I'd say look at every model because you can, right? And that way you're not going to be guessing as to whether the stepwise procedure has given you everything interesting or not, okay? And you can do that through this reg subsets command just by using method equals exhaustive. So you can do that. But, you know, let's be clear, if you've got even 7 or 8 X's, you're suddenly in a bit of trouble for that because the number of models is big, you know, it gets up over 100, 200, whatever. And then I think you start to look at these other methods. Truthfully, I wouldn't use forward or backwards on their own. They tend to miss good models unless you're lucky. So I'd always then use sequential replacement as the go-to technique, and that should hopefully produce you a model that gives you the right answer. Now it's always interesting if you have the time, and God knows you don't always have the time, to do all of them and see if they give you the same answer. They don't always. Okay, and that's just the way it is. So that's how I would run this thing. By the way, one thing I haven't talked about as we've talked through this is NBEST. So NBEST, I've just chosen in this particular example here to be 10. That's because there are only 15 models you can choose from. So 10 is kind of a little bit south of 15 and so on. If you're doing this for a larger example where you've got maybe 5 or 6 X's and you use NBEST equals 10, you're probably going to have trouble because it's not going to be able to look at enough models. So you probably, so as n goes up, I would be raising this number here, okay? So I forget how many X's you might have in the project, but I think it's bigger than 4. Might be 5 or 6, and for that I'd probably set NBEST as something like 100, just so you're clear, okay? But that's the number it'll go up to in terms of number of models it'll look at. So just so you don't run into the problem that you choose NBEST to be too small, it doesn't show you enough detail. So these stepwise procedures are pretty good. Pretty good. All right. Nothing particularly graphical about them, and so I wanted to go back and talk about a couple of different types of plots that will help you understand model selection in another way. So the next plot I'm going to show you is called an added variable plot. Okay, so the code is here for this particular data. So let me run you through how you do an added variable plot, pretty simply. I'm going to do it down here so that it's recorded. So this is added variable plots. Now, what added variable plots will do for you is they answer a particular question. And that question is, if I've got certain things in the model already, can I add a specific other variable? That's what they're there to do, okay? So they answer the question, answer whether a variable can be added if others are already in the model. Okay, so we're going to have an example. We're going to have a y, just a very simple example. We're going to have a y, we're going to have x1, we're going to have x2. Okay, so we're just going to play with those two for the minute. Okay, we'll amp it up a little bit in a few minutes when we add an x3 and an x4, but I just want to show you this. Okay, so let's go. Step 1. I want to fit y versus x1. I want to see if you can add x2 if x1's already there. So I'm going to fit y versus x1. And I'm going to create residuals from that model. Okay, so the first two steps are to do that. So how do I do that? I go model 1, mod 1 equals ln y tilde x, y tilde x1. Okay, I'm putting x square brackets 1 because I'm using the x's that I've got for this cement data. Okay, so that's the first x. Okay, and res1 is going to be the residuals from that model. Oops, equals model 1, mod 1 dollars to z. Okay, so there's the first two steps. Fit y versus x1 and then get the residuals from that model. Now let's think about what those are, right? Because it's all very well to have an algorithm going do this, do this, do this, but if you don't know why you're doing it, what's the point? So, what do these residuals mean? Well, they're the bits of y that aren't explained by x1, okay? So it's what's left to explain in y after x1 has got in there and had a go, okay? So let's make a note of that. These represent the part of y not already explained by x1. In other words, the part of y left to explain. Not explore, explain. Okay? So So that's what those residuals, that's what's left in y to be explained. All right, step 3. Now I'm going to fit x2, oops, I'll learn to type, fit x2 versus x1. And I'm going to create residuals from this model. That's going to be step 4. Fingers aren't working on a Monday morning. There we go, step 4. Okay, so let's do that. Mod 2 equals ln x2 tilde x1. And res2 equals mod 2 dollars residuals. Now, this is a bit of an odd step, right? Because so far you think, oh, okay, yeah, I fit y to x1, I've got the bit of y that's not explained by x1, that's cool, I think I know where this is headed. But now we fit x2 against x1, so what does this represent? Well, remember, one of the big problems in multiple regression is that the x's are correlated. In other words, they carry much of the same information. If the correlation's high, really high, they carry exactly the same information. Right? So what I want to do is I want to clear out the bits of x2 that x1's already got to. Right? So what do these represent? These represent the part of x2 that is not in common with x1. This is common, just using plain language. Part of x2 that is not in common with x1. In other words, it's the capacity of x2 to do anything beyond x1. Okay? So it represents the capacity of x2 to explain anything beyond x1. So now we've got these two things. We've got the part of y that still needs to be explained, and we've got the part of x2 that's capable of explaining anything, right? And x1's been cleaned out. It's cleaned out of both of them, okay? So what I'm going to do is I'm going to match those up. I'm going to match those up, all right? In a plot, I'm going to plot res 2 against res 1. And that thing's called an added variable plot. That's my added variable plot. So res 1, the part of y that still needs to be explained, is plotted against the part of x2 that can explain. Now if I see a pattern there, it means that the part of x2 that can explain is related to the part of y that needs to be explained. In other words, it's game on. I need x2 because there's a pattern. Now if there's no pattern, just blank, random noise, then it means y did not benefit from what was left in x2. There was no explanation, just noise. Okay? So this is called an added variable plot. The name is kind of obvious now because I'm trying to add that x2 given that x1's in the model, right? And it just matches up what needs to be explained versus capacity to explain. And if they show a relationship, then there's a need to add that next variable. So this is a really neat tool, right? This is a visual alternative to a t-test. Because what a t-test does is it says, do I need x2 given that x1's already in the model? That's all a t-test does for you. This is a visual alternative to a t-test. And look, with all the problems that t-tests have, right, all those assumptions, all that hand-wringing about p-values, you really want a visual alternative, something you can look at and go, oh yeah, there's a pattern there, okay? Now, if you want to do a third variable, then you do this same sort of thing, right? But now, you start with both x1 and x2 in the model. So, to see if x3 is needed, if if x1 and x2 are already in. How would we do this? Okay, so same sort of thing as before. Mod 1, the first model, is going to be lm y tilde, but now I add both x1 and x2 because they're both in. Right, so the idea is the same. Res1 equals mod 1 dollars residuals. Okay, so that's the part of y that's not explained. Part of y not explained by x1 and x2. Okay, so that's the first part, the bit that's left to explain. Second part, mod 2, is going to be lm x3 tilde x1 plus x2. Okay, and res 2 is going to be mod 2 dollars residuals. Okay, what's that? That's the capacity of x3 to explain anything beyond x1 and x2. So you clean both of them out. Okay? So same deal as before. You're trying to match up what you need to explain versus your capacity to explain. And the base idea is you clean out those other variables. They're out of the picture now. Okay? And now we plot res2, res1, and that's your added variable plot for x3, given that x1 and x2 are already in the model. Now, we know what's going on with this data set. We don't think you're going to need x3 if x1 and x2 are already in there. So we should see noise. We should see noise, and that's noise. Okay? Now, here's where your brain is working against you, right? Because there's only 13 dots on that plot. So you're going to see a pattern, aren't you? You're going to see some people I saw someone with their finger, which is excellent. I love it when people pull their fingers out. And I saw someone doing that. And you can kind of see that, but with 13 data points, this is pretty noisy. It's not a strong pattern. Remember the last plot? The last plot was a strong pattern. Everyone's going to see a straight line there. This one here. It's kind of noisy. If you didn't have one of these points, maybe the top one here that's guiding your eye, so let's put the cursor there so you can't see it. You see less of a pattern, right? If you remove just one or two of these things, the pattern kind of disappears. And so you probably don't need x3. So this is a nice visual tool, and it's another aid to model selection, right? So those are called added variable plots. Now, there's one other plot that's described in the notes. So I'm not going to really talk about it because I don't actually truthfully find them that useful. They're called partial residual plots. They're based on a similar idea. Before I move off added variable plots, let me show you all of the added variable plots for this particular data set, 1, 2, 3 and 4. So I'm going to go par mf row equals C22. I'm going to put 4 plots on the page. I'm just going to run through here. So these are the 4 added variable plots for this data. So this is the top one, the top corner, is you're trying to add x1 given all the others are in there. This one's you're trying to add x2 given all the others are in there. This is you're trying to add x3 given that all the others are in there. And this is trying to add x4 given that all the others are in there. Okay? So noise, 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 noise. In other words, if you've got 3 things in there, you're done. You're not going to add another one, right? So this is just checking that last variable in each case. But you can do it sequentially so that you're building it up the way we've talked about stepwise. All right. Now, one other plot just to talk about. I'm not going to focus on it because it's not something I find particularly useful. But another way that you can assess whether or not a variable belongs in the model is to do what's called a partial residual plot. So let me just describe the strategy. So what you do is you fit the model involving, say, x1, right? And then what you do is you clear out x1 the same way you did in an added variable. And then you add back in a linear term in x1. And then you plot the residuals of those two things, one against the other. And the idea is that if you get a straight line in that plot, then x1 should be linear in your model. So that's the theory behind it. The reason I don't use them is that if you don't know already that x1 belongs in your model in a linear way, you're probably in a bit of trouble at the get-go. You should be able to detect non-linearity much easier than doing these sort of complex residual plots. Okay? So I'm not going to recommend that people use these partial residual plots, which is why I'm not going to go through the code for them in particular. If you want to, you can look at it, but you're very welcome to ask me questions about it later if you want. But they're not things I recommend. My mainline tools for regression and for model selection are really, first of all, so now it's sort of talking a bit of strategy. The first thing I try to do when I've got a high-dimensional data set, this is going to sort of segue into project territory, because if you're doing the project and you've chosen the insurance data, you will be fitting a regression most likely. So we'll talk about the strategies you might use. So the very first thing I try to do in most data sets which are high-dimensional is you start with a scatter plot matrix, right? That is your first eyes on the data. In the same way as for simple linear regression, you always start with a scatter plot, right? So first eyes on the data are always a scatter plot matrix. And I generally add either low S curves or little straight lines to each panel depending on what you see, all right? That's your first eyes. Now, once you've made some basic determinations based on that, and generally speaking, if your data set is halfway reasonable, you'll see structure in there. You might not know exactly yet what to do, but you'll kind of get a feel for which variables are important and which ones aren't. But remember, that's not final word because these variables interact with one another. Okay? So you've just got to be a little bit careful. But you'll get, from that one plot, you'll get a pretty good idea of where you're headed. Okay? So that's thing one to do. Second thing I try to do, particularly if you're in a high-dimensional setting, so you might have one Y and you might have 5 X's or 6 X's or something like that, is I would try to see if I can reduce the dimension of the visualisation so that I can get a look at lower dimensional analogues of this space. So I'd start looking at things like symbol plots and coplots. Okay, so those are your next line tools, symbol plots and coplots. Now the golden rule in symbol plots, use a symbol whose dimension is the same as the dimension of the variables you're encoding. So if you're doing Y versus one of the X's and you're coding for a third one, if that third one is a continuous variable, use a little line segment as your symbol. That'll be a star. Okay? And the length of that line will represent the size of that third variable. Okay? If you're trying to encode, don't use a square, don't use a circle. Because remember, they grow bigger in area than the size of the object. Okay? If you've got two variables to encode, that's typically going to be the case. Use a rectangle. Width and height are going to be the visual elements that encode the size of those variables. You get more ambitious than two variables, you've got to be lucky, essentially. Right? But you can use stars then. Okay? Remember, the lesson we learned from our data here was if you've got a binary variable like survival was, use filled and unfilled symbols. You get that high contrast distinction. And then you can get an extra variable in the mix. Filled versus unfilled with rectangles, for example, will give you 3 variables. The binary variable plus 2 others, height and width of the rectangle. So try symbol plots. Coplots are another strategy. Again, coplots require you to think about that third variable, maybe divide it into high and low. right? Try not to be too ambitious. So, for example, if you've got a third variable and you want to encode for that in a coplot, and that, for the data we had, the survival data, it was an APGARS variable. So it had values that go from 0 up through 9, okay? And so you could do 10 coplots, one for each value of APGARS, but each one would have like 3 data points in it, so that's useless. So what we did was we went low and high, right? 0 to 4 was low, 5 to 9 was high. Try and do big cuts. And remember that your strategy has to be try something, if it works, great. If it doesn't, try something else. So if you're encoding in a coplot for that third variable, try high and low. See if there's a high contrast approach that works. If that doesn't tell you what you need, try low, medium, high. Break it into 3, okay? If you find yourself breaking it into 5 or 6, slap yourself. Stop, right? Coplots probably aren't going to work for you in this case, okay? So try basic structure first. Low, high, low, medium, high. Maybe go to 4 if you're desperate. If you go beyond 4, you're probably not going to get what you want. So simple plots and coplots will again give you some idea of multivariable relationships in low-dimensional visualization, so they're useful in that sense. If they don't get you very far, have a look at what principal components tells you. Okay? But remember, don't expect miracles. When people use principal components, they expect miracles, right? I'm going to run PCA, and it's going to tell me that it's going to unlock the secret to the entire data set. It almost never does. Okay? But it might. So it's like rolling a dice. So PCA is another tool you can use. All right. Now, once you've decided what sort of model you're going to fit, okay, then you can proceed to regression approaches. So you start with the full model, have a look at the summary. Right, as we saw for the cement data, the summary told us there's something going on here. Right? None of the p-values were smaller than 0.05, but there was clearly structure. So there was a problem. So then you've got a series of tools. So the tools I would use are added variable plots, maybe to visualise if adding a variable makes a difference. I'd probably then proceed to a stepwise regression straight away, because you know you can do these things manually, but stepwise regression will give you a quick cut at what's useful in terms of models and what isn't. And again, the go-to method is likely to be sequential replacement, unless you can fit every model, right? And can fit every model means either number of x's is small or number of x's is large and you've got a lot of time on your hands, right? Because the number of models goes up very, very quickly. And you'll very quickly, after this process, get an idea of what models are good and what models are bad. And then you can start to decide, well, which x's do I need, which x's do I not need, okay? Then, at the end, you're almost done. The last thing you do, once you've decided on the model that you're going to fit, is you're going to look at diagnostics, right? So you're going to look at diagnostics. Now, your analysis is not complete unless you do 2 things. First thing, you've got to show me the diagnostics. By diagnostics, I mean residual plots, QQ plots of residuals, leverage plots. These are the typical diagnostics, okay? So if you do the project or any assignment that involves regression and you don't put those in for your final model, not good. Not good. Okay? So putting those things in is important. Why is it important? It's important because I need to see that you've checked that your model's okay. All right? It's really important. Now, let's be really clear here, right? In your next life, when you're not sitting in a university class and you're doing real analyses, you still do the diagnostic plots, but you don't show anybody, right? It's really important to recognise that. So for me, yes, you do the diagnostic plots and you put them in, because I need to see that you've done them. But when you're out in the real world, they're for you, so that you can decide whether the model's good, bad or ugly, and then you proceed. You don't share those with the boss or whatever. Your boss should assume you've done them so you know the model's right, but your boss don't need to see them. And they certainly shouldn't end up in the annual report. right? Because diagnostic plots, to anybody who doesn't know what they're looking at, are frankly really confusing, right? What are these residuals? Why are you plotting them? What is this QQ plot? What does Q even mean? Oh my God, right? It's complex for people who don't know what you're talking about, all right? So, you need to show me these diagnostics. So, we ended up, after our model selection, we ended up with a model that had X1 and X2 in it. That was the best choice. So that's our final model. So I'm going to go ahead, fit it. There's the summary of the fit. So you always show me the summary of the fit, but more particularly, you tell me what the model is, right? So in your assignment, you have to then, at the end, tell me what the model is. Y equals coefficient 52.6 plus 1.468 times x1, okay, plus, which is CA3A, okay, plus 0.6625 times CA3S. And that's your model. Now, always write your model down. Always write your model down. If you don't write your model down, guess what? It's like you've read to the second last page in a book and then you stop. And you don't find out who the murderer is. Why are all books about murder? I don't know. You don't find out who the murderer is. You don't find out how the book ends, right? You all know, right? You go to the movies, the credits are rolling, you stick around because there's always something at the end. You know that, right? Yeah. Make your assignment like this as well. There's a cliffhanger, all right? Don't leave people hanging. Put the model in. Put the model in. So that's thing number one. If you don't put the model in, bad news for you, okay? Thing number two, this is a favourite. A lot of people, when they write down the model, is they write down this thing and then they go plus error. Don't write down plus error. Why? Well, because the model's been fit, right? There's no error. Errors are with data. Errors aren't with your answer. If you go plus error in your answer, it's like saying, well, this is my answer, but I could be wrong. So I'm going to put plus error in here. If you put plus error in the final model, people have every right to say, I do not trust you at all, right? Because you said this is the answer or something else. And that's no good, right? So, never write plus error here. There's no errors in fitted models. There's errors in unfit models. Okay? So don't write plus error. Now, the other thing you'll notice is I didn't write x1 here and I didn't write x2 here. I gave the variables their proper names. And that's because people like to use the names of the variables because then they know what they're talking about. Okay? In fact, I probably shouldn't have said y. I probably should have said heat because heat is the response variable. So I should have said heat is written as a linear function of this chemical compound and this chemical compound. Okay? And so I end up with that kind of model. So always tell me your model. And now let's go ahead and do these diagnostic plots. Now there are 4 diagnostic plots you're going to want to show me, which is really nice because they fit in a nice grid. So the first thing you're going to do is 2 by 2 array of plots. Leave some room in the margin so that you can put titles on. Okay? So let's go ahead and do that. All right, first plot is the leverage plot. Now remember, what's the leverage plot? The leverage plot takes that hat matrix and it takes its diagonal values and it shows me the heights of those particular values. Remember how leverage works. If a point is a long way away from the other points in the x direction, it can lever the model all the way through it. So that's what leverage is for. And you'll notice that this plot has this horizontal line whose height is at, in this case, 2 times 4 on 13. 2, that 2 is always there. The 4 here is the number of x's. There are 4 x's, okay? 2 times p on n, 13. That's where you put your reference line. And you can see there's one point that's just a little bit above the line, so we don't worry. Generally what you're looking for, pardon me, what you're looking for here is a point that's sticking way above the line. If there's a point way above the line, then you've got problems potentially. This looks fine. So that's the first one to do, is your leverage plot. Then you'll typically do the QQ plot of the residuals. Okay? Things to remember about QQ plots. A, they've got to be square, right? Because you're comparing like with like. So par PTY equals S makes it square. Then you go QQ norm, residuals of your fit, title everything up, then you put your QQ line in. And this is quite interesting, right? You look at that QQ line and you look at the points, you can see they're pretty much on the line. For 13 data points, this is as good as it gets, right? You don't expect 13 data points to line up perfectly. It just ain't how it works, okay? Small number of data points, you generally don't get a nice line. When you're done, put PTY back to M so that your next plot's not square, all right? Then the last two plots are your fitted values versus your residuals. So we'll put them both there, and then add a low S curve to those fitted values versus residuals. Now, remember back to simple linear regression. When we did simple linear regression, we didn't plot residuals versus fitted values, we plotted residuals versus X, because we only had one X, right? Well, now we've got four X's, and we don't want to have to do four plots. So what we do is we combine those X's into fitted values, and we put that on the X-axis of this plot. So the residual plot here is you plot the fitted values versus the residuals, okay? Now, that should look like random scatter. You shouldn't see that kind of funneling shape, because that's heteroscedasticity. You shouldn't see curvature. You should see random scatter, and that looks pretty good. Then we do an absolute residual plot. In other words, we fold this plot around 0, and we run a low S curve through it. And if that low S curve is pretty flat, then we go, cool, right? We fit our model, we think we've got constant variance. And again, you know, we've got 13 data points, and this is about as flat as you're ever going to get for 13 data points, right? So that's pretty good, and we're kind of done. Okay? Now, one very last thing, when we wrote down the model, go back up here, we wrote down the model here, one thing you might want to do, so let's just grab this line again, so copy that. I'm going to have a look at the summary of the fit again. Remember that all of these things have standard errors, okay? So when you do write down the model, best practice would be to write down the standard errors. So there's your model. Then what you do is you come through underneath, and underneath each one in brackets you can type the standard error. 2.2, whoops, 2.28, 9. Come over here, then 0.121. Right, just in brackets underneath the number. That looks nice. 0.045, 046. Okay? So if you want to be really complete, then you would add the standard errors underneath. And again, look, it depends on your audience, right? If you're showing this to people who know a bit about statistics, it makes complete sense to put in standard errors, right? Because a statistician knows what a standard error is. But if you're showing this to your grandmother, maybe leave the standard errors out, right? Because Granny don't know what standard errors are. Well, maybe she does, but odds are she doesn't, right? And so you leave these out because Granny just wants to know what the model is, right? Why you're talking to your grandmother about cement, I don't know. But all families are different, right? So it's good. And that takes you basically through the analysis process. Now, the key thing to remember about all analyses is at the start, you don't know the answer, and at the end, you think you do. Okay? That process is not a straight line. We talk about straight lines all the time, but that process is not a straight line. Your ideas about what's going on change as you look at different visualisations, as you try different models. Okay? Remember we talked the other day about the garden of forking paths? The idea that every analysis involves lots and lots of choices? That is what you do when you run an analysis. Okay? It is not the case that someone gives you a data set, you fit a model, you write down the answer. Done. 10-minute job. If that is your experience, you ain't doing your job properly. Okay? The process of model fitting, the process of model validating, the process of visualisation is deeply iterative. It is all about trying things, making mistakes, fixing up where you went wrong, trying again, until you get to something that you can convince yourself is close to right.